if we're talking about the fine-tuning argument, I take the fine-tuning argument to be a sort of an extension of a very basic, it's not even an argument, it's just kind of an instinct. Why do most people who've ever lived and still live believe that there's a God? Well, one of the reasons might be if you look around at the universe and there are various bits and pieces of it that seem to fit well together in a way that you might think, needs a mind.
Any sufficiently advanced technology is indistinguishable from magic.
Dr. Luke Barnes joining me in person in an undisclosed location for undisclosed reasons. We've been brought together. Do you expect me to believe that, Mr. Bubba? Mr. Barnes, Dr. Barnes is a lecturer at the University, I always forget, University of, is it Western?
It was the University of Western Sydney, and then they paid a lot of money to change it to Western Sydney University.
You know how much consulting fees they had to pay?
Oh, yeah, right? I don't want to say.
Did you change mascots from the fighting?
I wasn't there, thank goodness.
From the fighting wallaby to the dingoes. It's a pleasure to meet you in person.
Yeah.
We last spoke together about 2 years ago for a previous book of yours called The Cosmic Revolutionary's Handbook, which laid out the case for sort of proponents of alternatives to the standard Big Bang cold dark matter cosmology, what they would have to do to overthrow it, overturn it. And maybe we'll start there. How does it feel to have your book utterly obliterated by the forces that have proven based on JWST data that the Big Bang never happened? How do you feel, Luke? Will you ever recover from that devastating blow? Or what's your take on it in all seriousness?
I think collectively, a lot of cosmologists, so what we're referring to, JWST results came out, and a paper, an article came out from Eric Lerner, and this was treated as something new, something dangerous, something's going to overthrow the establishment. Panic. Yeah. And without going into it too much, basically, it's the same objections to the Big Bang that he published in 1993 without a lot of changes. There's two things to say about it. One is there's been plenty of, this isn't a secret, there are plenty of online people who are in cosmology who responded to those critiques. Weigh them up yourself. And the other thing is it wasn't really about the Big Bang. It was about the physics of how galaxies form. So at worst case scenario, we need to rethink the way we think that matter collects into galaxies in the universe. But it didn't really touch the expansion of space, the hot Big Bang, the real pillars of the Big Bang theory.
Yeah. When we look at the Big Bang, previous books of yours, including with your former advisor, right? So the Cosmic Revolutionary's Handbook is Geraint Lewis, your former advisor, and who's at New South Wales. Is that right?
Sydney University.
In
New South Wales.
In New South Wales. It's so confusing. It's everything's upside down. We had a conversation recently as well, but you also wrote a book prior to that. With him, and remind me the name of that, Luke.
It's called A Fortunate Universe, Life in a Finely Tuned Cosmos.
So I thought we'd start there. A lot of the discussions that we've been having this week with eminent scientists from around the world tend to involve around things pertinent to biology, chemical life formation, the improbability of forming a lipid cell structure and eukaryotic life, and so forth. Very stimulating. I wouldn't say this positive one way or another, but oftentimes we look at the universe and we're told it's extremely finely tuned, and that no secret would lead to the title of that book, A Fortunate Universe. Fortunate implying some teleological purpose and maybe some ultimate beneficence of something or someone or some force. So what is fine tuning, first of all? Where does it come from, and what is the weak anthropic principle WAP, and how does it all come together in the cosmological argument?
So the nice thing about that book with Geraint was I'm a Christian, he's an atheist. We wrote that book together, and most of it we wrote together. The last chapters are sort of debate about what it all means. But on this fine-tuning issue, here's what a Christian, a theist, and an atheist can agree about the science. So he interprets fortunate as lucky in the context of a multiverse. But the thing we agree on is something that's turned up in the physics literature over the last sort of 40 or 50 years, where there are these fundamental constants of nature. When we boil things down, as we love to as physicists, to the deepest equations we can find, there are some basic properties of the universe that just need to go into those equations. How heavy is an electron? How strong are the forces between them? And into the standard cosmological model. What's the ratio of dark matter to baryonic matter, ordinary matter? What's the value of the cosmological constant, which is causing the expansion of the universe to accelerate? They're just numbers. Just that you can look them up. There's some number that all of these are. And what's been just sort of discovered almost accidentally, or certainly it wasn't expected over the last 50 years, was as theoretical physicists asked, what if we change them? We don't know why they are what they are, so let's at least ask the question, what if they've been different? You find universes which are perfectly mathematically fine, as we can write equations down and we can solve those, but for a number of those constants over the range in which the equations are fine with them, what you might think is what's possible, you only get an interesting universe like this, which has any sort of structure in it at all, including life, for a very small range of the constants. So this is called the fine-tuning of the universe for life. And as I said, two scientists who have very different beliefs about what's really underneath it all can at least agree on what happens when you change these numbers.
Yeah, we'll get into hopefully the discussion of what fine-tuning is, how it could be accomplished in a moment. But before we do, recently I've been reading some work by Fred Adams at University of Michigan, and he's been on the podcast, although I think I may have deleted the recording by accident, Fred.
We'll do it again.
It was before I became such a pro, as you guys can all tell out there in internet land. I want to do it again, because he is a phenomenal thinker, and he was at UC San Diego visiting his close colleague George Fuller, who's a good friend of mine. And in his most recent papers, which I believe will be a book, supported, I believe, by the Templeton Foundation, if I'm not mistaken, which is kind of ironic, because Templeton Foundation tends to support things that seek synthesis, if not harmony, between science and religion. And some people have a problem with that, be that as it may. Fred argues that, no, in fact, some of these wide-ranging phenomena are actually broadly tuned or coarsely tuned. For example, he sets the stage, which is the first comment I'd like you to make. When we apply our perspective from the weak anthropic principle, we're necessarily filtering out a whole host of variables to concentrate on a select few variables. And his kind of rubric, he looks at stars. What would it take to form stars? Gravitational forces, electromagnetic forces, nuclear forces. And he finds there's a huge parameter space, to use his words. It's not improbable at all. First of all, I want to ask you, is there necessarily kind of an anthropic bias when you search out, well, what does it mean to be finely tuned? And then second of all, how do you react to his claim that, no, the universe ain't so finely tuned after all?
So first of all, Fred's doing absolutely first-rate work on this. It's really great and really helpful. I've tried to sort of follow a little bit in his footsteps, and so I've published a few papers on this as well. One way I would summarize some of his work is to say that stars turned out to be more robust than we gave them credit for. So in the early fine-tuning literature, this goes back quite early, actually. It's in 1970, I think it's a paper by Freeman Dyson, who said...
First guest on the podcast.
Oh, wonderful. If I've got it right, I might have it wrong. Anyway, in our universe, if you take a proton and you smash them together, they will not stick to each other. Those two will fall apart. The way the sun operates is you take a proton, smash them together, and you hope that in that instant where they're close to each other, thanks to something called the nuclear weak force, proton turns into a neutron, and proton plus neutron will stick together. What Dyson had argued is that if you had a very small increase in the strength of the force that sticks those two types of particles together, you could actually stick a proton and a proton to each other. And if that happened, stars would be explosive, because now it's really easy. You don't have to wait for the weak force to turn one of them into a neutron. Proton, bang, you just blow everything up. What Fred pointed out quite rightly is that that's not true. A star is what we call a thermodynamic system, where the micro details of reaction rates are actually controlled by the overall balances of heat and energy flowing. So you won't get an explosive star. You'll simply get a star which is cooler in its center and will react appropriately to the fuel it's got to power itself. So actually, you can have perfectly long-lived stars in those sorts of universes, and this is what needs to happen in this fine-tuning anthropic principle kind of investigation. We need to know what happens when these constants change, and sometimes, because it's not our universe, we're thinking about weird alternatives. Sometimes we get it wrong and we just have to rethink it, and Fred's done some great work. So stars turn out to be more robust than perhaps we thought. I think there is in fact one way he discovered where stars can fall apart in a way we didn't think of before. If you look at his 2008 paper and you change the strength of electromagnetism, there's a famous plot in there. Well, I say famous, I've looked at it a billion times, where we knew stars would be in trouble if electromagnetism was too strong, but it turns out there's a way they could be in trouble if they're too weak as well. It's a two-sided thing there. But in general, yeah, stars are quite robust. You can sort of hope in any old universe you might get stars to fire up and be long-lived. The main driver of the lengths of the sort of lifetimes of stars is really the strength of gravity rather than the nuclear. For a wide range of parameters, the nuclear the nuclear reactions will adjust. But overall, I think that there's still very strong cases of fine-tuning that we've done, calculations again and again and refined them, as Fred's done, as I've done, and as other people have done, looking more deeply. And they have retained their, look, here's a set of possibilities and it's only a small subset where life can exist. So yes, of course we keep doing calculations to refine it, but I wouldn't say this is just any old universe.
And when we look at the overall kind of sieve that physicists apply to the observations and then select out certain components that we think are dispositive or might be dispositive towards the origin of life and evolution of life, I find it, sort of the physical constants are almost the easy part. And I kind of make an analogy towards, COVID-19, and it's one of our first, it's the first time we're meeting in public, and it's the first, some of the first in-person podcasts I've had the opportunity to do.
Yeah.
And I think back to 2019 when we were building the Simons Observatory, which is my ongoing project with 300 collaborators around the world, including some in Australia. You'll be pleased to know. And we're putting it together. And to do that properly, we had to have a analysis of risks to the project. And so we had things like the Chilean peso might fluctuate against the euro, which is where we build some of the hard metal works that we have. And then concrete comes from Bolivia, and maybe there's shipping challenge, whatever. There's some fluctuations, and there's stochastic processes. You could model those, and it could be a strike, and you could even have some punctuated things. Wow, it happens in South America. You never know. Yeah, these experimentalists, we have to be quite on top of things from many different angles. But one thing we didn't have, no one had, was global pandemic shuts down the world for 2.5 years, causing things like, my graduate student, I can't just say to her, see you in 2 years, I'm going to stop paying you now and come back in 2 years. No, we had to sustain it. So we did. But it's sort of to bring up the notion of these punctuations, these radical things that occur in order for there to be life on Earth, and why we think that the physical properties of the universe are the most contingent. And so I guess, if you had to select a few, kind of from your studies of the fortunate nature of the universe, what are some of the ones that speak loudest to you of some perhaps, organization of the universe? I don't want to say designer. If you want to, it's fine. But how do you, what do you feel are some of the most pertinent and calculatable properties of the universe that we can draw some conclusions about how fortunate we are or not?
Yeah. Because we're at the level of fundamental physics, and we're trying to go from these fundamental constants up. Actually, it's really hard to do calculations right from the bottom up to anything, even from quarks to protons. This is all the stuff you discover when you start digging in. That's really hard. And then protons to nuclei to atoms. So what we really focus on when we try and do fine-tuning work is is there it's sort of the reverse of the question you asked, is there a real disaster somewhere in space, in possibility space, parameter space, that's going to help, that's going to be obvious that, okay, no structure over there? And some of the more obvious ones are, if you look at the masses of the fundamental particles that we're made out of. So famously, there's the electron in our atoms, that thing going around the outside. There's up quarks and down quarks that make protons and neutrons. So how heavy are those? And there's a number there. It's very small in any sort of kilogram scale. And then the sort of particle physicists get to work saying, what happens if you start changing these numbers and you map out the three-dimensional space, and you can see it mapped out in the book. But some of the really interesting kind of disasters are things like, if you change the numbers, that say the masses of the quarks in a certain way, you end up that the lightest kind of particle that you can make out of three quarks, right, is not the proton or the neutron, it's something else. It's a 3 up quarks, called the delta plus particle. If you're in a universe where that's the most stable thing you can make out of the quark, here's a problem. You could, through very simple energy arguments, come to the conclusion that a delta plus particle will not stick to another one ever, right? And so suddenly your periodic table is gone, because that proton sticks to neutron, sticks to everything else. That's how you build up all the nuclei on the periodic table. Suddenly all you've got is a particle with the charge of 2 electrons, so it has the chemistry of helium, which is to say no chemistry at all. And suddenly you've got a universe where it's just so drastically simpler than our universe. If you want to write a chemistry textbook, there's one element in the periodic table, there's no chemical reactions. That's a pretty easy textbook to write, except there's nothing to write it on or with. And so it's those sorts of cases where, once you start to see those sorts of things inhabiting big swathes of the way the universe could have been, you start to really think that, okay, there's something interesting going on around here. 92 stable elements in the periodic table, the chemistry of carbon. We've really got it going on around here. Another one that cosmologists will be more familiar with is just the cosmological constant. It's a famous, there's called the cosmological constant problem, which says, we've discovered in our universe something that's making the expansion accelerate. So galaxies are not just moving away from us, they're moving faster today than they were yesterday. And what could be doing that? Well, it turns out in the way we describe the fundamental structure of particles around us, we use things called fields. So an electron is really a sort of ripple in an electron field. And if it were the case that even when there's no particles in a particular place, there's still some energy there, that would cause the expansion of the universe to accelerate. It has that effect on that gravitational effect on space-time. And if you then use a kind of calculation that we can do in other places in quantum field theory of how does the structure of the vacuum, the structure of the field when nothing's there, when no particles are there, how does that structure, add up to an energy difference? You end up with a rough calculation that would predict an enormous value of the cosmological constant. And that's a problem, because it's another very easy way to make sure there's no structure in the universe, because space would expand so fast that no particles are ever near each other. So even if this proton and this neutron could come together to make something, they're a trillion light years apart. Mm-hmm. And it's these sorts of disasters where, okay, we can debate structures of stars. There's some really interesting edge cases and complicated cases, but there's some real proper disasters waiting us out there in sort of the ways that, according to the best physics we have, the universe could have been, but isn't.
Are any of the arguments, you think, capable of convincing somebody, of the existence of some sort of overarching teleological purpose for these? Or do you think, there'll always be sort of room for doubt? I spoke to Jim Tour at this conference earlier in the day and asked him, as a someone who is practicing but might be considered agnostic myself. I do practice in contradistinction to people like Freeman Dyson, who was called himself agnostic but didn't do anything different than Freeman Dyson. Then Richard Dawkins didn't go to the same church that Freeman Dyson didn't go to. But wondering, is there any kind of hope of convincing people? I usually feel like I don't engage in debates because science isn't done that way, and also because you never change your mind. Like, I don't know if you guys have prime minister debates in Australia. I assume you do at some level.
They're a bit pathetic.
Yeah, but we never change. Oh, Trump made a great argument. Let me just, I'm going to vote for him. I don't find him objectionable at all. But how do you view this? Is it sort of just people wanting to vent their own ideas without any help of really convincing the other side, or could you see your faith strengthened or maybe weakened by an argument, either on your side or on maybe an opposition side?
Yeah, the one thing that all of this, so I started looking into this sort of almost by accident during my PhD. The one thing I can't predict is how people react to it. It's kind of hilarious. One of the reasons Geraint and I wrote a book on this is because I wrote a review paper in 2012, and then so people asked, "Oh, could you do a talk on that stuff? That looks interesting." Just at the at Sydney University, where I was at the time, and the department turns up, give us just pretty standard talk. Geraint was there as well as everyone else, and then something happened that I've not seen before or since, which 45-minute talk and an hour and a half of questions afterwards. Everyone just sat around, which is amazing because it was lunchtime, but no one left. And not just that there were questions, but immediately people had not just opinions, but different opinions. And so someone would ask a question and someone else would answer it. And then someone else would reply to that. And so it wasn't just people wanted to get information out of me. I'd laid the ground rules. And now everyone wanted to talk about what this meant. And I've seen that again and again and again in as talking to, I've talked in churches, I've talked in like skeptics in the pub groups, all sorts of, amateur astronomy societies. And more than any other topic I've ever seen in my life, people just immediately are like, either this has got to mean something, or I know what this means and I have to tell everyone. And yeah, it just has that effect. And I love it for it, because I love, the physics is wonderful. How this affects this and that affects that, and these equations, it's beautiful. And then just the way it lights people up. And so there's every reaction to this under the sun. I mean, me personally, I already believed in God. And so this was sort of, I don't have a problem here. I've heard of someone else who did a talk on fine tuning, and then someone in the audience said afterwards, "Look, I don't believe in God. I'm not religious, but something weird is happening here." And I think that impression is sort of there. But what I love about it is people can't sit still in their seat. It just draws opinions out of people.
You have to have an opinion. Apologize for the siren sound in the background. There's some carabineri somewhere chasing after somebody. I call them the carbonari because they're always trying to get me more pasta.
Some wine emergency up the mountain.
That's right. We've been out of Reno. Stop. There's no more. So getting back to sort of more, in the technical side of things that your research is concerned with is actually not these topics. You're actually practicing as a theoretical cosmologist on a daily basis. You were talking earlier in the week about a course that you're teaching maybe for undergraduates where you get into actually philosophical arguments, but not necessarily pertinent to God or anything like that. So
not at all.
Can you talk more about your teaching? It sounded very interesting, and we talked a little about quantum mechanics, and does Aristotle have anything to do with quantum mechanics? What is the role of the ancients? Because in my conception, Aristotle basically has the highest ratio of fame to number of things he got right. I can only think of one thing that was absurd. I mean, you could have discovered just by dropping this, and I'm not going to do it, but dropping these two things at way very different amounts back then, that they don't hit the ground at the same time. The one doesn't fall faster than the other, as he presupposed.
Now do it with a leaf.
Oh, okay, I'll do it with a leaf.
Right.
I'll go to the moon.
Well, so this is, there's so many wonderful things to talk about there.
Yeah.
Let me start with the teaching. I got put in charge of a course at Western Sydney called Scientific Literacy, and all the first year science students take it. And what it was a number of things. It was sort of, welcome to university. Here's how to do well. And here's how to reference properly and research properly. So let's just make sure all that's good. Don't plagiarize and all that sort of stuff.
Don't.
How to how to write properly, which is something I'm actually quite passionate about. How to give a talk properly, and then there's a real chance to take a couple of lectures just to say, what's this science thing? What are we actually doing here? And there's two approaches that I take there. One's a very, very rapid history of science broadly construed, where that I don't think science, by one definition, science started with the scientific revolution, but on a more broad, let's try and understand the world we live in. It's a very human activity. So we have experts in Australian Aboriginal astronomy at Western Sydney. So I was able to get one of those experts, Ray Norris, to give a 20-minute talk on that, which was really fascinating. We can talk about that if you want. But the Babylonians and the Greeks so getting onto Aristotle, I have a very high regard for Aristotle. Part of that comes from a few things. There's a wonderful book. The man's surname is Leroi, and I suspect it's not pronounced Leroy, but maybe something French that's equivalent to that. It's called Aristotle's Lagoon, and he read all of Aristotle's immense works on biology, and as a modern biologist, we could sort of try to untangle the logic of why he thought that. When he's wrong, why is he wrong, and what does he get right? And there is a remarkably hard, deep thinker and a close observer of nature in Aristotle. This idea that he just sat in an armchair like this.
No, of course. I mean, but that's the paradox of him. So the one thing that sticks in my mind that he got right, maybe in the Lagoon, was that whales are mammals, not fish, as people had thought for millennia, right? So therefore, he was aware of the observational component of the pre-scientific method. And just to, rebut, just to be a little bit more harsh on him than I know you are. I'm a big fan of his too, but let me just say that, it's not like Galileo had like the Large Hadron Collider available to him to, he dropped a couple hundred miles from here. He dropped some objects that were available to Aristotle from a height available to Aristotle, did the observation, said no, and did a thought experiment. If you have two masses connected by a string, are they one mass of a given weight? No. So you could do the thought experiment or the actual experiment. And it seems to me that Aristotle did neither. Not condemning him, but what can we learn about the scientific method from somebody who was often, at least in the physical sciences?
Yeah, that's a crucial question. That's a very good way to put it. I think here's one of the things which is logical if you're Aristotle, but with hindsight actually causes a lot of the problems. He made a distinction between natural motion and violent motion. So if I drop something and it falls to the ground, he's saying, well, it's made of earth. Earth's natural place is at the bottom of the universe, and so it's seeking out its natural place. If I lift it back up again, that's something violent I'm doing. I'm moving it away from its place. And so that requires an agent. If you think that, then experimentation is violent motion. You're not seeing nature. You're seeing what you're interfering, right? We think of, and it's so natural to us, when we say, if you drop two things with different masses, they fall at the same rate. And the thing you have to remember is that what we're putting in brackets after that is in a vacuum. Now, Aristotle, didn't believe in a vacuum, but more importantly, that's not a very natural state, right? Let's suck all the air out and then see what happens. And Aristotle would be saying, well, of course you're messing with nature when you do that. If I just take a piece of paper and a rock, they fall at different speeds. That's the thing we want to explain. And so I'd say it's amazing how subtle little things like that shape so much of the way that you move, that you view the world. There's another thing which is sometimes pointed out. All of these are a little bit oversimplified, but whereas Plato was a mathematician, Aristotle wanted to classify things. So he didn't want to measure, he wanted to classify things. And that probably comes out of, actually, at heart, he's a biologist. And if you see nature, you don't immediately, I don't see that tree and immediately want to start counting the leaves. And I don't think if I went to all the effort, there'd be some beautiful mathematical law there. And so that emphasis on what I need to do to nature is classify, the thought that if I really went and measured some stuff, I might discover some laws there is something that takes a while for people to realize that can be done.
So soon they'll be calling us for another 2,000 calorie helping of pasta and bread, which Luke and I want to partake of. So let's do a little bit of rapid fire kind of questions. And just playing off the last topic we just talked about, Aristotle. If you give your students a set of books, only one set, would you give them or her the collected works of Aristotle or the Feynman lectures on physics?
Oh, I have to say Feynman.
Okay.
There's two brilliant minds there, of course. Yeah. And I mean, I don't want to say that they're just as good as each other. No, look, the last couple of thousand years, we really have learned some stuff about the way the universe works, and it's more. I'd like to think Aristotle would want Feynman's books as well.
Certainly would have a lot to glean from them. One recapitulation on the fine-tuning problem. So, Sean Carroll has passed multiple time guest on the show, as you are now joining the pantheon of two-time guests on the show.
Bad John.
He said, there's no need for God. It's a theory that's barely useful, or maybe one of the least useful. It's still a theory. It's still there's no need for it. And in that context, he and I talked a long time ago about, take the standard model in his book, The Big Picture, and you say, where are these couplings and which couplings could couple to an agent? And there's really nothing in there that could do that. And I phrased it a little differently when I spoke with Stephen C. Meyer a couple of almost 2 years ago now for his book, The Return of the God Hypothesis. Said, how does an intelligent agent instantiate, is there some knobs, and when does he and like Judeo-Christian said, when does he start in the manipulation? Is it like at the BBN phase, forming elements? Is it at the stellar evolution phase? Is it at the genetic evolution phase? So how do you think of it? Like, how does the tuning get done?
I mean, if I had to, nail me down on something, I think the initial conditions. So there's a wonderful quote from John Wheeler in his book At Home in the Universe. Actually, it's a collection of essays, but it's in there somewhere, where he says nothing is clearer it's paraphrasing, but almost nothing is clearer in physics than what is and what isn't physics. So the laws that govern the way particles move, yes. The initial velocities, no. Right, the initial conditions are really something else. Right. So if you're that choice that you have to make there between, say, the way I view the world and say the way Sean views the world is, I assume if you're Sean, if there are something like initial conditions, they're just the start of explanations and that's it. So he has there's a quote from his that I use a lot because I think it's very clear, which is his view is that there is a chain of explanations in the universe which reaches the ultimate laws of nature and stops. And part of those laws of nature would be just initial conditions or boundary conditions or whatever they are.
This is Wheeler or Carroll?
No, sorry, Carroll. Okay. Carroll said that. And so, either the choice is not between, do you just let the universe run itself or do you have someone sticking their finger in? It's whatever these initial conditions are they just it? Or do you think there's some cause deeper than that in reality?
So maybe I'll close. I usually have 4 existential questions. We only have time for one. So in Sabina Hassenfelder's most recent book, Existential Questions, or Existential Physics, which you got from my topic, calling things existential questions, I'm sure. You are referred to, and I want to appropriately reference the quote. But first, let me preface it by saying the progenitor of the name of this show is Sir Arthur C. Clarke, who came up with the phrase, the only way to determine the limits of the possible is to go beyond them into the impossible. But another thing that he said is, when an elderly but distinguished scientist says something is possible, he is very likely correct. When he says something is impossible, he is mostly wrong. I want to ask you, as described by Sabina as a middle-aged scientist, you're not elderly, but you are distinguished. I won't say the other adjectives she describes you by, but that's just her favorite curmudgeonly way of doing things. What have you changed your mind on, if anything?
What have I changed my mind on? So
in science.
No, I'm going to say what it was. We had a discussion it's on YouTube. You can go and find it. And she said something reporting on this later, said something along the lines of Barnes turned out to be a big-faced middle-aged man with
Brown
a beard,
face.
brown face, or whatever it was. And I cut that quote out of the book. I got the book and then put it on my Facebook page, and everyone who knows me thought that was the funniest thing they'd ever seen. It's probably got the most likes of anything I put on any social media platform. So thanks. I laughed my head off. That's fantastic. What have I changed my mind about? I grew up Young Earth Creationist. That's the background that I grew up in. That was the church. But in Australia, where it wasn't. So, for example, there was a debate between the pastor, who happened to be my father, and the local science teacher at the local high school, who also went to the church, but on the validity of evolution as a theory. And people turned up, and it was quite. I just remember it being quite cordial. And it was fine, and it wasn't like people ran him out of the church or something. So it seems odd to say. You have to sort of say this in the American context. It was Young Earth Creationist, but somehow not dogmatic.
Right.
Over the course of then getting, I was good at maths. Obviously, I'm now an astrophysicist. Going to university, learning physics, discovering that astrophysics is the best, and then being able to actually look at the claims that had been made by Young Earth Creationists about the age of the universe, realizing they all fell apart in my hands when I had the ability to look at them for myself. So that was, and then the reason that didn't affect sort of my Christianity was that the most that follows from that is not God doesn't exist, but I've misunderstood it. 2 chapters of the Bible, which there's plenty of chapters of the Bible I misunderstand. So that wasn't a major sort of moment, but that was quite the process. I mean, that was quite the years of digging into this, that, and the other, and trying to understand.
And I salute you for having the courage, as we like to say, to go into the impossible. It takes a lot of courage, and you're renowned for both the clarity of your presentation, your explanation, and the fact that you do so much outreach to the public. I really salute that. I have a, canard. I always say, we scientists have a moral obligation to share what we do with the public. So, and I think we have a venal financial interest as well, because if they don't understand what we do, they're going to stop supporting us. Right?
Yeah.
Anyway, Luke, it's been a pleasure to meet you in person. I have to have you come back for a part 3. Thanks, everybody. Subscribe to follow Luke on all social media links. We'll have those in the bottom. And do tune in next time for more exciting content on Into the Impossible. Thank you so much, Luke.
Thank you.
Any sufficiently advanced technology is indistinguishable from magic.